Now, the purpose of this class is to apply calculus to functions that have multiple inputs and multiple outputs. And so what we want to discuss is just some visualizations for these functions. You're already good at one case where a function that has one input and one output. This will be our notation for functions. This indicates there's a function whose name is f. So this is just the name of f. And this symbol, the bold r, stands for the real numbers. And so when we have r to the n, we're talking about a list of n real numbers. And the function starts with a list of n real numbers and ends with a list of m real numbers. Now, we're going to want to come up with visualizations for these functions. The most important cases are where we have either 1, 2, or 3 inputs and 1, 2, or 3 outputs to our functions. Now, a lot of times, if a function has multiple outputs, the output is technically a vector. We'd say that it's a vector-valued function. And so we would a lot of times write the name in bold. So this function, since it has 2 outputs, we might call it bold f. So or you give it a bold name so that people know that the output of that function is a vector. Sometimes a function that has only one output, since a single real number is also called a scalar, sometimes we call them scalar-valued functions. So you hear that term sometimes. This one is scalar-valued because there's only one number that comes out of it. So versus a vector-valued function. A lot of times, if there's one input and 1 or 2 inputs and 2 or 3 outputs, then we actually can think of these as parametrizing or parametrizing a curve or a surface, so giving your location as a function of time, or giving you locations on a surface as a function of 2 freedoms. So a lot of times functions like this, the name that we'll use will actually be bold r. We're thinking that r is a vector that takes us radially out from the origin to our position. So that's some of what's going on with the naming conventions. Now, the case that, of course, we're most familiar with is this case where there's one input and one output. And the visualization that we're most frequently used to is having the one input be on the horizontal axis. Usually we call it x, and one output being on the y-axis, and then we look at the graph of the function. So each point here represents an input paired with an output. So that's a graph. But there are many other visualizations that are possible. So we mentioned the graph. That's one. We're going to look at 3 basic kinds of visualizations that we're going to emphasize. Remember, a graph is a special term that we're going to use. So we have a function, we're going to have techniques for visualizing it. If we use the special word graph, we mean a visualization that includes the inputs and the outputs together. Now, if you look at these functions, if you're going to have the inputs and outputs together, then you're going to have to have as many axes as you have inputs and outputs. So, for example, if you have a function from R1 to R1, then that takes 2 axes. If you have a function from R1 to R2 and you wanted to look at the graph, inputs and outputs together, that would take 3. But if you had a function from R1 to R3 and you wanted to see the inputs and outputs together, you'd have to do that with 4 perpendicular axes, which, living in a 3-dimensional world, we're not used to doing. So the graph would be good anytime the number of inputs and outputs is something that we can visualize. So we're used to having 3 perpendicular directions, and so we can look at the graph in each of these cases. Although in this case, there's probably a better visualization which we've seen, which would be as a parametric curve in the plane. So let's see. So graph is just one way. You can see it only works if the sum of the dimensions is not too large. So another thing, if you have functions over here that have more inputs, another thing you can do is just visualize the outputs. For example, in each of these cases there are either 2 or 3 outputs and only 1 input. So that means that this would work really good in each of these 3 cases. When you have as many inputs as outputs, then then all of the outputs of the function are likely to fill up a volume in the space, or to fill up sort of a region that's kind of hard to see. But when the number of outputs is less than the number of inputs, and you just focus on when the number of inputs is less than the number of outputs, and you just focus on looking at the outputs, then you can see some interesting things. So, for example, here we've already seen this already. A parametric curve. Let's just do a line, x equals 2t plus 1, y equals negative t plus 3. This is an example of a function, if we put these together into a single function r that has one input and two outputs, x and y, right? Or we could write r of t equals, r actually gives back a pair of numbers, x of t and y of t. Now we know that that's going to draw some kind of parametric curve, right? So this is what we're talking about. When you look at the parametric curve, you're only looking at the x and the y values, right? We're not really seeing the input, but we know that the curve is going to be swept out in particular directions, so we can imagine that as t increases, we're moving along the curve in a particular way. And so we're not really seeing the inputs, but we're seeing their effect as the inputs move, as the input moves us along along this curve. Now we could have a function like this, but that had three outputs, so that would just give us a location in three-dimensional space. So instead of getting a curve in the plane, we would get a curve in space, or a space curve. So we could look at just the outputs x, y, and z. Since we're taking a single number t and turning it into a three-dimensional location, for each time there's going to be one location. You can see as we change time, then we're just going to get a one-dimensional curve in three-dimensional space. So we're thinking about r. You could think about that as the vector that would carry you from the origin to your location, and as a function of time. So as time changes, the head of this vector moves along and sweeps out or traces out that space curve. Okay, if there were multiple inputs, so maybe two inputs with three outputs, so we get out from those two inputs, we get an x location, a y location, and a z location. Now, since there are two freedoms, you can see if you change u, you'll move one way. If you change v, you'll move another way, and that's going to create some kind of surface that we'll see. So we can look at the surface, which would just be looking at the outputs that come from this parametric surface. A third way of visualizing a function is just to look at the inputs that lead to a certain output. Let's look at an example that you're probably familiar with. If I write down the equation x squared plus y squared plus z squared equals 1, you know that that's a sphere of radius 1, right? It's not really a function, although it does define the one variable in terms of the others. For example, you could solve for z, but this really wouldn't be a function, because if you solve for z, you have to consider plus or minus value in this square root, which means for each pair x and y, you have two possible values of z, right? Which makes sense. If this is the x-axis and that's the y-axis and this is the z-axis, then for a certain point in the xy plane, there's a point on the top part of the sphere and a point directly below on the lower half of the sphere. And so there are two z values that go with each one. So this doesn't define z as a function of x and y, right? It's not giving us a function. It is multi-valued. So for each input, there can be more than one output. But we could think about this as being a level set of another function. So if we had this function, w equals x squared plus y squared plus z squared, when we're talking about the sphere, and we couldn't visualize this function, right? We couldn't look at its graph anyway, because we have three inputs and one output. So it would take 4 dimensions to visualize the graph of this. But we could visualize the set of inputs that lead to a particular output. For example, if we want to know, so this function w Do you see how it has 3 inputs and it has 1 output? The 3 inputs are x, y, and z, and each x, y, and z pair gets turned into or mapped to a single number w. So don't need parentheses if it's a single number. Okay, so this is an example of a scalar valued function, right? So we have a function from R3 to R1. We can't look at the graph of that function, but we could definitely ask, okay, what are all the possible values of inputs x, y, and z that lead to w equals 1? So, well, that would be the sphere of radius 1. What about all the outputs that lead to 2? That would be the sphere of radius square root of 2, and so on, right? So even though we can't see this function's graph, because we can't visualize things in 4 dimensions, we can still look at the level sets of this function. In this case, for the function w, the level sets are concentric spheres, and that gives us information about the function. So those are the 3 ways that we'll look at. We'll try to visualize functions. If we can look at the graph, or we can look at just the outputs. That will be when we have fewer input dimensions than output dimensions. Then we have a parametric curve or surface. That will work. If we can't do the graph or parametric curve or surface, then we can look at level sets. So just remember, when we talk about the graph, we're talking about inputs and outputs together. That's a special kind of visualization. The parametric curve, we're just looking at the outputs, or a parametric surface, although we might put arrows to indicate as we increase t, for example, what direction are we moving along the curve. And we could look at all the inputs that lead to a particular fixed value of the output. Those would be level sets. So as we go through, what we're going to do now is think about these 9 different types of functions that are of interest to us in this class, and we'll go through and come up with visualizations that work or that would be useful for each one.